Good morning, everybody. It is Wednesday, the 13th, and we are moving along in our chapter or semester review. As a note, though, I want to tell you, a lot of you are sending me emails about your grades and stuff. Your best way to help you, the best way you can help yourself, is to go back through your grade book, and if you have any assignments that you haven't turned in, get them turned in, get them done, get them turned in. Okay. We're making special allowances because of this whole online thing. So do them complete, right? Don't just turn something in. I give you grades. I'm fair with everybody. I give you grades based on what you turn into me. Okay, so get those. Remember, I've always said all year. I've told you guys anything is better than a 0. Okay, so. If you have a 0 in your grade book, those zeros there are not to knock your grade down, really to show you, especially during the whole online thing. That was our policy. Those zeros, we put them in there make it easier for you guys to see. Okay, if you don't put the zeros in, it's just that dash and it doesn't affect your grade. So we put the zeros in there as a red flag to remind you to get those turned in. Okay, so anyway, if you have any questions about that, please let me know. All right? So let's move on with Chapter 10. Energy. I always enjoy this chapter. Okay, Chapter 10 was all about energy. A lot of stuff, we've done, like I said, energy is also in the other sciences. And you're going to see it again. Energy, you'll see it throughout your life. This is all information that you will be able to use and have in your knowledge banks, in your brain, okay, and memories that will help you to, navigate through issues that you come upon as you go throughout life. Okay, so this basic stuff. Energy is the ability to do work or produce heat. Right, produce heat. Right, heat is energy. Right, it's the temperature is the kind of like the kinetic energy, right? Temperature of something it's the potential, right? Even though that's not the best description, but it's the state. Okay, it's how much those atoms are bouncing around in whatever test device that you're working with, a chamber or anything like that. Okay, so let's see. That which is needed to oppose natural attractions. That's what you need energy for, right? Conservation of energy. It can't be created nor destroyed. You can only convert it into another form. Okay, we have what we have. The energy in the entire universe is constant. It's changing, right? Stars are exploding and creating, and we're doing stuff here. I'm talking right now, spending energy, right? And it's all this throughout the entire universe. The energy that is there is constant, but it's changing. Okay, the universe only has, as far as we know, the universe only has so much energy, right? And it changes its form, but the amount of energy doesn't change. Okay, potential. That's the energy due to position or composition. It's waiting to happen, right? Loaded for bear, ready to come shoot out of the out of the blocks. Okay, so let's see. Kinetic energy is that energy released. Okay, the tip off for a basketball game. Everybody's standing on there. The ref's got the ball ready on its fingertips, ready to toss it up in the air. The two people that are jumping for the ball are they're all coiled up and ready to go. And then that ball goes up in the air and bang, kinetic energy. Energy's happening. Okay, so here's the example. The ball has potential, and when he lets go, it's kinetic, and it hits that ball, right? Also, remember, you got to think about things too. Be smart. You have to be complete. As this ball, as it's rolling down the hill, it is it's rubbing, right? Remember, I rub my hands together, and you feel your hands start to warm up. That's happening in the ball as it actually, even though it's rolling, it's still that contact, right? It's got that ball, the energy that's in that ball has to get it to down that hill, right? So, and there's centrifugal energy there going on, right? And so the ball is actually losing energy as it goes down. It's a small amount, but it's still losing it. And that's a great example of enthalpy, okay? That's what's happening. Okay, so let's see. After the ball is rolled down the hill, now A has very little potential. B has not all the potential, but some, right? It has more potential than A. Okay, so, and that's the example of the nature of energy, okay? So heat involves the transfer of energy, all right? So temperature is the amount of energy in any one spot, like the state, right? A state function, okay? Something that, let's go ahead. You guys remember most of this stuff. Work is force acting over a distance. That work is that ball rolling down the hill, right? It's working as it rolls down the hill, okay? Energy is a state function. Work and heat are not, okay? Heat can build up, okay, and then or you lose heat or gain heat, right? And work is the path that it's taking, right? It changes independently of its pathway, okay? So, state functions. Distance traveled from one location to another is not a state function, okay? So, when that ball's rolling down the hill, that's one state that it's in right now. Then it rolls down the hill, and that is the next state. It's where it's at right at that moment, okay? So that is the state function. That is the state function. It's not dependent upon the path that it takes, okay? State function is a change in elevation, okay? So if you go, remember I used the driving your car from your driveway here down in the valley going up to wherever you go, you travel, you're going to expend energy and that gas is going to go down. So when you get to point B, when you leave point A, your driveway, you get to point B, okay, the amount of energy, your car is hotter, you've got less gas, okay, so it's got more energy, and that heat, right, remember heat is a transfer of energy, that's energy transferring. That's the temperature of your car dissipating it, and that's the whole enthalpy thing, okay? We'll touch on enthalpy at the end of the PowerPoint here, okay? So, temperature and heat. Temperature is the measure of the random motions, all right? The temperature of this box is 90 degrees C, and this one is cold water, so you can see the little jets behind the molecules aren't as big on this side as they are on this side, showing the motion, right? The motion is a lot more, these molecules here have more energy, and they're hotter, right? So now heat is the transfer of that heat. So this heat wants to get out and get to the cold water, right? So the cold is drawing the heat over. So remember, that's kind of vice versa, right? So the cold is drawing the heat over, and so that energy transfer, and eventually, both as you level out, once both sides are the same temperature, in this case 50 degrees Celsius, right? Because the potential is 100, right? So you've got 90 and 10, right? That's your total energy. Okay, when they even out, when they're both at 50, then there's no draw. There's no attraction for the heat to transfer from one to the other. Okay, they're both stable where they're going to be. Okay, so heat is the way in which thermal energy is transferred from a hot object. Heat always transfers from hot to cold. Okay. Then we also looked at exothermic and endothermic processes, and to do this we used a model of a system and its surroundings. Okay, the system is a part of the universe on what you're focusing on. It could be your body, it could be your car, whatever that system is that has got potential energy, right, and kinetic energy as well. Okay, so, and then the surroundings. I'm a system that I'm releasing sound energy or acoustic energy into the environment. Okay, and that energy is going out in actual, it's acoustic energy. Okay, sound waves. Okay, waves of energy, and that's going out and being transformed into other things. Right, your ears are picking it up, and you're hearing it, and you're converting it into internal energy. So your ears work and they vibrate, and that mechanical energy of your ear drum vibrating, right, and the cilia and all that stuff, all the workings of the inner ear. Those of you going into anatomy physiology next year, you're going to love that. It's going to be pretty cool. So But anyway, that's what's going on. So that's your body is taking the energy that I'm expending in acoustic sense, in acoustic waveforms, and your body is converting it into mechanical and then biomechanical, right? So, or biochemical, biomechanical, and you are able to hear it, and your brain gets the electrical signal, and you process it, and you understand what I'm saying, blah, 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 right? And we're all good. So, all right, so moving on. So, exothermic, exiting, energy exits, okay? Energy, so heat is direct transferring out of this system. That's exo. Endothermic is the vice versa, okay? Endothermic, heat flows into the system, absorb energy from its surroundings. Exothermic is the process of energy flows out of the system. Energy gained by the surroundings must be equal. Whatever energy I'm putting out is all that can be absorbed by who's ever being influenced by my voice, okay? So, and then here's a bunch of examples, okay? The PowerPoint is in the module, so if you want to, really, if you're serious and you want to really remember this stuff, you open up that PowerPoint and you can go through these. And if you have any questions about any of them, let me know. I'm here, okay? We're still in class. This is a review. It would be a review for the final, but even though you're not taking a final, we still need to review this stuff. It's important that we do what we're doing this week, okay? Alrighty. So there's the answers. So these concept checks are great, right? The system and its surroundings give the direction of the transfer. Okay, methane's burning in a Bunsen burner in a laboratory. Okay, so what's it doing? Methane is burning inside the Bunsen burner, okay? All right, so let's see. Thermodynamics is 10.4, okay? The relating to heat. Thermo relates to heat. Dynamics is the mechanics of it all, the workings, the motions of bodies under the actions of forces, in this case energy, right? It's the study of energy. Once again, we talk about the conservation of energy, where you can either create or destroy. And again, these are kind of like the, if you want to call it the Bible for energy, right? These are the commandments, right? Energy in the universe is constant. Law of conservation of energy is often called the first law of thermodynamics, okay? Then I've also tagged a video on here that you can go watch if you want to about thermodynamics. Okay, so internal energy, right? And the internal energy of a system is the sum of kinetic and potential, right? And this is the formula that we used where the delta, right? The delta change in energy is equal to the heat plus the work, whatever's happening. If you lose some of this, your energy goes down. Lose any of these, right? If you lose heat and your work remains constant, your delta's going to go down, okay? So, all right, sign reflects the system's point of view. In an endothermic process where energy is going out, Q is positive, okay? So, where no energy is coming in, heat is coming in. Endo is into. If heat is going out, then it's a negative. You're losing energy, okay? Or losing heat, okay? So, and here's an example of that, all right? So, internal energy, the work is on the surroundings. So if your work increases, you're gonna lose more energy, right? Your system does work you work and your heat goes out, and you're gonna lose energy. Okay, heat is going to go out, exothermic. So, and here's another. This one takes practice. This concept needs some practice, right, for you to fully understand it. So, once again, you can use these PowerPoints it gives you the answers. You can think about it. It gives you the answers, okay? All right, so measuring energy, calories in joules. Okay, calorie is the amount of energy. This is the standard, okay? Remember the lowercase, right? The uppercase C is 1,000 of these, okay? It's the amount of energy required to raise the temperature of 1 gram of water 1 degree Celsius, okay? And in joules, that 1 calorie, the energy is in joules, 4.184 joules. Okay, that's the standard. Okay, convert 60, right? So you go from cal to joules. Okay, so 1 cal equals 4.184 joules. And then you do the math. You do your dimensional analysis, okay? So measuring your energy changes. Specific heat capacity, right? Each element has its own specific heat capacity. Okay, and then this was the formula that we used for it, right? We went through all this formula, changed these variables. It was easy once you guys got the hang of it.